Hello all, welcome to the video lecture. This is Ramesh Lama. In this video lecture, we will be discussing about the architecture and operation of multi-layer neural networks and derived equation of backpropagation used to train them. Well, first we will see the model of an artificial neuron. The neural networks are interconnected perceptron-like computing elements called the artificial neurons. And these neurons performs the same computation as perceptron, but they differ from the perceptron in how they process the result in the computations. Well, as we have discussed in our previous class, the perceptron uses a hard thresholding function that outputs +1 and -1 to perform the classification. Suppose that in a neuron of perceptrons, the output before the thresholding or the weighted sum, here we can see the weighted sum, this is infinitesimally greater than 0. And when thresholded, when we threshold this sum or this input, the very small signal will be turned into +1. But similarly, the small signal with the opposite sign would also cause a large swing in the value from +1 to -1. And we know as the neural networks are formed from the layers of computing units in which the output of one unit affects the behavior of all units following it, the perceptron sensitivity to the sign of a small signal can cause serious stability problems in an interconnected system of such units, which makes the perceptrons unsuitable for the layered structure. And in order to solve this problem or this stability problem, what we can do is we can change the characteristics of the activation function from the hard limiter to a smooth function. And in order to do that, we use this function, and this function is nothing but it's called the sigmoid function. It is like here for the given input z, and this z is nothing but the weighted sum of product of the input x and weight w, or we can say it as weighted sum of the input. And what we do is we take 1 upon 1 plus e to the power minus z, and this gives us neuron or the artificial neuron like this. We can see this, it has a weight, this wij, and az, the activation function or the input, and we have got the output. This is the activation function, or which is h, and this h z is in the form of this formula, or it is the sigmoid function. And let us see how it looks like. It does nothing but it squashes, or it squeezes the line varying from -infinity to +infinity into the interval of 0 and 1. We can see the output varies from 0 and 1, and it crosses 0.5 at the origin, and then it flattens out, and it's appropriate for classification, because we would never want to make a prediction greater than 1 or less than 0. And the most important thing is it's differentiable, and with the very simple derivative, and gradient descent can be done on the sigmoid function. So let us see how its derivative is estimated. This is our original sigmoid function, which is 1 upon 1 plus e to the power minus z, and we take the derivative of this function with respect to z. So this is the h prime z gives us the first derivative of this sigmoid function. And if we apply the quotient rule, then this quotient rule results into with the quotient rule, this sigmoid function results into this expression, where we can see that it is 1 upon 1 plus e to the power 1 plus e to the power minus z whole square into e to the power minus z, and we can just split it, this e to the power 1 plus e to the power minus z whole square into 2 1 upon 1 plus e to the power minus z into 1 plus 1 upon 1 plus e to the power minus z, and this e to the power minus z remains same, and this we can further factorize into 1 upon 1 plus e to the power minus z into 1 minus 1 upon e to the 1 minus 1 upon 1 plus e to the power minus z. And what we can see here is that this is nothing but the original form of the sigmoid function, and which we can write as z. And another here again we can see 1 minus 1 upon 1 plus e to the power minus z, which is also the sigmoid function. So the final result will be hz, which is sigmoid function, into 1 minus hz, which is also the original sigmoid function. So the gradient of sigmoid function is expressible on its original form, that is hz into 1 minus hz, and we will use this function in the gradient descent in the backpropagation algorithm, because as we have seen before that the gradient descent, while doing the gradient descent we have to estimate the gradient of the error, and it will come in use on changing the parameter or on updating the parameters. And another function is the tan h function. It's also same as a sigmoid function, but it's bound to range of -1 and 1. It's also similar to the sigmoid function, and the gradient is stronger there for the tan h than the sigmoid, and this is fx for the given function. Like fx, we can say that 2 upon 1 plus e to the power minus e to the power minus 2x, and this tan as x is equal to 2 into sigmoid of 2x minus 1. And while talking about the gradient descent, there is one problem which we call the vanishing gradient problem. This usually occurs in the stochastic gradient descent or other form of gradient descent, and like while doing this stochastic gradient descent, it becomes very small, or the signal becomes so approximately small that the signal registers as 0, or gradient based on method learn the parameters w value by understanding how a small change in the parameters value will affect the network's output. And if a change in the network if the change in the parameters value w causes very small change in the network's output, the network just can learn the parameter effectively, so that will create the problem. Or the large change in the value of parameter for early layers doesn't have a big effect on the output. So like we can see here, the vanishing gradient problem depends on the choice of the activation function. We can see that the activation functions squash their input into a very small output range in a very nonlinear fashion. In our previous slide we saw that how the sigmoid function squashes the value. And for example, the sigmoid function maps the real line into the small, like in the range of 0 and 1, and the large regions of the input space which are mapped to the extremely small range. Even a large change in the input will produce a small change in the output, hence the gradient is very small. So the first layer will map a large input region to a smaller output region. which will be mapped to an even smaller region by the second layer, which will be mapped to an even small region by the third layer, and so on. So the large change in the parameters of the first layer doesn't change that output much. So the lower layers of the network trend very slowly because the gradient decreases exponentially through the layers. So we call the vanishing gradient problem. And the main problem is like the lower layers of the network trend very slowly, and it may because of the gradient decreases exponentially through the layers. So in order to overcome this problem, there is one option which is known as the rectified linear unit ReLU, and this, as the name suggests, it is a rectifier, or it's based on the rectification of the signal. That means the rectification means it will when we give the input, the output will be like it will give the output only when the input is positive, and the negative input will become, all the negative input will be 0, or it will not pass the negative inputs. So the output, the input directly if it is positive, otherwise it will output 0. So we can express it in terms of, for the given input x, this ax will be max of 0 and x. This means only the positive input will get the positive output, only the output will be same as input if it is positive, otherwise it will be 0. And it doesn't have the property of squashing the input space into the small region, and gradients at the positive values become constant and they do not vanish anymore. So it is also nonlinear in nature. The range of ReLU is in the 0 and infinity, and as we know that sigmoid or tan edge will process all the activations to describe the output of the network. We can use these functions at the output of the network, but it doesn't activate all the neurons at the same time. As you can see, like for the input with the 0, less than 0, it will give the output 0. So it's sparsely activated, or the sparse network is faster than the dense network. And it's also one advantage is it's less computationally expensive than tan edge and sigmoid, because it involves simpler mathematical operation. So this is all about the ReLU, but there is also one problem. Like we have got the input x. For the input xn, the input to the rectifier can be written as, like, this is the weighted sum of the activation function in previous layer and the current weight. Like we have this input to this Zn. This is nothing but the input to the rectifier, and it is based on the weight and the activation from the previous layer AIN for that particular input xn. The rectifier neuron function is, as we have just seen before, it will be max of 0 Zn. And to estimate our for the gradient descent, what we have to do is we have to first estimate the error. This error is nothing but we take the difference between, in very simple form, we take the difference between the current output, which is ReLU here, and this this is the target output y. And in order to take the derivative, when we take the derivative of this error with respect to Zn, or this input to the rectifier, it will be del n. That means it will be 1 when Zn is greater than 0, and it will be 0 if Zn is less than 0, means when the input to rectifier is positive, we will get the derivative of this error with respect to this input as 1 and 0 when this Zn will be 0, because here we can see this error is equal to Zn minus 1 or Zn minus y if Zn is greater than Zn is greater than 0, and it will be like it will be 0 minus y if Zn will be less than 0. And when we take the derivative with respect to Zn, for this we will get 1, because Zn the derivative of Zn with respect to Zn will be 1, and minus y, because y will be constant, so it will be 0, so it will be 1 if Zn is greater than 0, and otherwise it will be 0. So this derivative of error with respect to Zn will be 1 if Zn is greater than 0, and it will be 0. And similarly, if we take the del error, which means the error with respect to w, or our parameter weight, and using the chain rule, we can express it in the form of del like the derivative of error with respect to Zn into derivative of this Zn with respect to weight, and it will look like this. It will be del n into an, because when we take the derivative of Zn with respect to omega, we will get this a and j. And now, if for input xn, the current weight put the ReLU to left side of the flat side, while it optimally should be on the right side for the particular input, and the gradient is 0, so the weight will not be updated. We can see here, like this is the ReLU, and we can see we can see here on the left side and the right side. And if if the current weight puts the ReLU on the left side, means on this side, that means when this Zn is negative, then we can see the gradient will be 0. This is our gradient. In both cases, we can see the gradient to be 0. So when the gradient is 0, and we cannot, in case of gradient descent, we cannot update our weights, because the previous weight, when the gradient will be 0, the previous weight and the current weight will be same. So there will be no update in the weight, or we cannot change the weight value. So for whatever the reason, the output of ReLU is consistently 0, then the gradient through it will be consistently 0. Then the error signal back propagated from the later layers gets multiplied by this 0. So no error signal ever passes to the earlier layers, and the ReLU is dead, or we call this the ReLU has died. And this problem typically arises when the learning rate is set to too high. When we set the learning rate too high, that will make a big change, makes big swing in the weight in the value of this ReLU. So this kind of problem will arise when we use this particular type of error function. So this is called the dying ReLU, and in order to solve this problem, what we do is we put a small slope for the negative values, and instead of altogether 0, this is called the now the ReLU will be max of instead of 0, we just multiply this x or the with the sum fraction. We just put the sum fraction, and it will increase the range of ReLU function. and activation is not sparse anymore. Now the activation is not sparse anymore, and now the function will look like this. Like this was the original ReLU, where the output will be same as input only when the input is positive, and it will for positive value it will be same, but in case of negative value it will multiply, or it will not make it completely zero, but it will give some portion or some fraction of the input, of the current input, and in this way the dying ReLU can be the problem of dying ReLU can be overcome. And another activation function is most widely used activation function is the softmax function, and as we saw, ReLU should be only used in the within the hidden layers of the network neural network model, and the output layers for the output layers, softmax function is used for the classification problem to compute the probabilities of the classes, and it calculates the probability distribution of the event over n different events, and this function will calculate the probabilities of each target class over all possible target classes. And after that, the calculated probabilities will be helpful for determining the target class for the given inputs, and the target class will have the high probability. Let's see the simple example here. This is the softmax function. It also squashes the outputs for each unit to be between 0 and 1 in terms of probabilities. Here is our input to the softmax function, and what we do is we exponentiate this function, and for 3.2 is converted to 24.5, 5.1 converted to 164.0, and minus 1.7 converted to 0.8 after the exponentiation. And after this we normalize all these values, and it gives in terms of probability distribution, and the sum of all probabilities will be equal to 1, and the output of the softmax function is equivalent to the categorical probability distribution, and it tells the probability that any class are true. And for this we can see this is for class 1, 0.13 probability for class 1, and 0.87 probability for class 2, and 0.00 probability for the class 3, and it tells the probability that any class are true, and it is used for the multi-class classification. And as we have seen here, what we do is we take the exponentials, we first exponentiate this value and we normalize it. And training the softmax function can be used for training a network to recognize and classify handwritten digit from images. It's just for the simple example. Suppose this is the handwritten digit, and the network would have 10 outputs unit, one for each digit 0 to 9, and if an image of the number 4, like this figure, the output unit corresponding to the digit 4 would be activated. And we can see here the digit 4 also looks somewhat like 7 and a little bit like 9 without a loop completed. So the most probability is seen at that it's 4, but also some probability that it's 7 or 9. So we can see here probability of digit, like for 4 we will get the highest probability, and for 7 and 9 also we get some little bit higher, but not like 4. So the softmax can be used for any number of classes, and it is used in the output layer of the classifier where probabilities are desired to define the class of each input. So choosing a right activation function, like we can see that sigmoid function and their combinations are generally work better for in case of classifiers and classifiers output, and sigmoid function and tanh functions are somewhat avoided due to the vanishing gradient problem. And ReLU function is general activation function and is used most of the cases these days. And if we encounter the case of dead neurons in our networks, the leaky ReLU function is the best choice. And the ReLU function should be only used in the hidden layers. We'll discuss about this about the hidden layers and the backpropagation in our subsequent classes. So as the rule of thumb, we can begin with using the ReLU functions and then move over the other activation function in case of ReLU doesn't provide with the optimum results. And the softmax function is ideally used in the output layer of the classifier. So these are all about activation functions. And next we will see about the fully connected layers in the next video.